So what are we doing? Did so we have done the this conditional expectation. We have defined the uh, definition, right? The definition conditional expectation with respect to sigma algebra, right? That is what we have done. Yeah, conditional expectation with another random variable also. Yeah, we have done this part and ah, and then we have defined this. We have done this part. Right? So yeah, so we have done this thing. And so conditional expectation with respect to sigma field. Okay, so in a sense the so here we are defining conditional expectation with respect to sigma field, and here we are doing conditional expectation with respect to a random variable. Okay, and and uh, and in a sense that we can always do then sigma algebra generated by a random variable, right? I mean, this is basically is nothing but uh, is I mean xy are random variable, and we have seen what is sigma algebra generated by a random variable, right? And another thing is the uniqueness we have defined this way, right? I mean, mm, so this is our uniqueness. If x1 equal to x2 equal to almost surely, then expectation of x. Uh, so this is the thing. So naturally, this will be again. You can think of it like this. So uniqueness, notion of uniqueness is like if x1 equal to x2, almost sure. Right? For random variable, it is always almost sure. Then x1 uh, uh, given we can write this is equal to expectation x2 almost sure. Or in a sense, or in a sense that yeah, uh, so this is the notion of uniqueness for conditional expectation. Okay. And so this is the uniqueness and conditional existence of conditional expectation. I just want to say we'll mention the result. We'll not go in detail. Okay. So for the existence part, so existence for existence part, I mean, um, there is a called there is a theorem called Redon-Nikodym theorem. Okay. So this theorem is very much complicated. I mean, not complicated. It requires certain uh, measure theoretic proof, and I mean, it needs certain soft measure theoretic this thing. So we'll definitely not go in the proof of the this thing. Okay, but what we will we'll just state the result. Okay. We'll just state the result. So what this theorem says that mm, this be a probability space. Okay. And let G be a sigma pool such that G is contained in. So this is called sigma. This is subset or it is called contained. Okay, contained in. I mean, A is contained in B, like we write it this way. Okay. Then for any random variable, okay, x, there exists a G measurable random variable such random variable y, or such that integral over a x dt equal to integral over a y for I mean, in a sense that so you have a sub-sigma field of f, and x is a random variable over f. X is a f measurable random variable. Okay. So we have seen what is f measurable. The inverse image will be part of the sigma algebra of this f. So what is f measurable random variable? So x is f measurable random variable. And you consider some set A, which is a element of G, which is also a set which is an element of the sub-sigma algebra. So naturally, A is an element of G. That means that A is also in F, right? Because G is contained in F. So G is a smaller sigma algebra which is in F. So something in G, that means that it will also be in F, correct? And so something in G will automatically means it will be in F, right? And so the Redon-Nicotin theorem says that uh, so that integral over the f measurable random variable x over a, that I mean there exists, so there will exist a random variable y which is g measurable, which measurable with respect to the smaller sigma algebra, and over a they will, I mean over a they will match if you take the integral. So so in a sense, so over a it will match, right? I mean uh, uh, so 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 what, so in a sense that you see, if you see the definition, if you see the definition of this thing, of the conditional expectation with respect to this thing. So this is the definition we were writing, right? Omega f p be a probably x be a random integrable random variable. This then for any a belongs to J, G, expectation of x given conditional expectation is a G measurable, and for any in G, this equality holds. So and here in the Redon-Nicotin theorem says that there exists a G measurable random variable. So there exists a G measurable random variable y, okay, such that integral x dp equal to integral y dp over the set A. And if you see the definition here, this definition, so basically what it says, so this is basically the y, right? So this is basically y. From the Redon-Nicotin theorem, whatever you are saying, that there exists a random variable y such that this happens. And if you see the definition here of the conditional expectation, that this conditional expectation of x given g, this is a random variable. So conditional expectation itself is a random variable, right? So Redon-Nikodym theorem says that there exists a random variable, g measurable random variable, and why such that this happened. And from the definition, you see that mm, this this expectation of x given g, or conditional expectation of x given g, is nothing but that random variable one, right? Because that what it says, that there exists a G measurable random variable y such that this equality holds. And here you see from the definition itself that expectation of x given G is nothing but G measurable. So y is G measurable. There exists a G measurable random variable y. And so this is my y, and integral y dp is equal to integral x dp. So this is the Redon-Nikodym theorem. So in a sense, that Redon-Nikodym theorem gives the existential part of the conditional expectation, and the uniqueness is this one. Uniqueness is this one. This is the uniqueness. So in a sense, that if conditional expectation with respect to a sigma algebra or random variable exists, I mean they exist and they are unique. Okay, so therefore, this is an important, I would say, this is an important theorem, but we don't omit the proof, because the proof requires a lot of this thing, but this is just for sake of, uh, just in sake of, I mean, your knowledge purpose, that you know that conditional expectation exists. I mean, if it exists, then this is unique. Okay, and the existence of the part comes from the uh, comes from radar decoding. Okay. Uh, so yeah, so this is mm, yeah, so this is one of the things that Nicodeme theory gives the existence of the thing. And now we'll do certain properties of the conditional expectation. And yeah, we'll talk about such properties. So, um, Now let's do certain examples or something. Uh, mm, so let G is equal to empty set and omega. So in a sense, this is the trivial sigma algebra, right? E is um, this is the trivial sigma algebra, correct? And then expectation, so this is this thing. This is so yeah. So G is so G is trivial sigma algebra. So so from the definition of the thing, from the this thing, from the uh, for any A belongs to G, right? For any A belongs to G. Now if I take my G to be G contains only these two elements, right? G contains only these two elements. So in a sense that what it will be. So for the definition, you see, for any A belongs to G, the conditional expectation this dp is equal to integral over A x dp, right? Now my G has only two elements, right? So over so I have to integrate over omega one, right? X dp, and this is what? This is nothing but by definition expectation of x, right? Expectation of x is nothing but the integral of x over capital omega d, correct? Right. And right. And so so we have to show that this equal to this almost surely, right? And so yeah, so from the definition integral over a, this equal to integral over a existing. So I can write that actually. I can write uh let me write that. So so here, so solution. Here A is equal to either empty set or omega, right? Now integral over A this is from definition integral over A. Correct. This is from the definition. From definition. This is my definition. I'm right. Now when A is equal to omega, then omega expectation x dp, right? This is equal to expectation x dp. This is nothing but the expectation of x because that is the definition. And this one again, I can expectation of x. This is a real number, right? So this we can write integral over omega expectation of x dp, correct? Because so this is something real number. You can take it out, right? You can simply this is a real number. You can take it out, and integral over omega dp is p of omega, and that is 1, right? So that's nothing but I mean integral over omega dp is nothing p of omega, and this is nothing but 1, right? So that we can, and then again the second part that we can have over null set. This is equal to integral over null set x dp, right? This is nothing but 0, right? And this is also I can write similarly over null set expectation of x into d. Because this one will again come as probability of sorry probability of null set, which is nothing but 0. So this is, I mean, sorry, I can write it little bit more. So integral over null set dp. This is nothing probability of null set. This is nothing set, right? So what we have shown that so what we have shown that integral sorry, we have shown that integral expectation x given g dp is so a equal to either phi or omega is nothing but a equal to phi or omega is x. So that is what we have shown in both the cases, right? So correct. Right. So we have shown this. So this implies that expectation of x given g is equal to x almost sure. Almost sure. Sorry. No, sorry. No, what we have shown, I have a mistake. We have a mistake. So we have what I have shown is just so. uh, so that is what I have shown, right? That both the cases I have shown that this integral over if a equal to omega, then this is expectation of x dp over omega, and if a is phi, now empty set, a is empty set, null set, then also this is we are shown. So that is what I have written. So this, so yeah, uh, so in a sense that so this actually this uses certain results. So for I mean for anything, so if you have integral some x dp equal to integral y dp for any two random variable for any two integrable random variable x and y, okay, x and for any two integrable random variable, then x equal to y almost sure. So this is a result. This is an important result. I mean, uh, this is an important result. So if you have two random variable integrable random variable, then if you have integral x dp equal to integral y dp, then x equal to y almost sure. So in fact, we have another result we can state in this regard that I mean this integral. Okay, so yeah, I mean so suppose integral over some set A. Uh, so so that A is an element of the sigma algebra. And this equality will be almost surely. So you can write it like this for almost uh, are almost purely for, or we can just, we can for almost, sorry, for almost every small omega in A. Sorry, for almost, which is the element of it. Which is the element of it. In fact, we have another result. So another result I can state here. So let omega f p, okay, this be a probability space, and let G be um, sigma field such that G is contained in F. Is contained. If you take any random, if Z is G measurable, so Z is G measurable random variable, and for any B, which is the element of G, integral over B Z dp equal to 0, then Z equal to 0 almost 0. So this is for any B in G. Okay, for any B in G. Then for any B, and G is a sigma field, sub sigma field of. So in a sense that then G equal to 0, Z equal to 0 almost surely. And here Z is nothing but X minus Y. If you see, I mean, what I have stated earlier, here Z is equal to nothing but X minus Y. Right? This is nothing but X minus Y. And another thing is uh, and this example, what we have done is so here you have the trivial sigma algebra, either phi or omega, right? I mean, so when you have this, this is the thing, and this is the thing where integral, this is equal to expectation of X, and this is 0, right? I mean, so in a sense that uh, so in a sense, in this example, you can see that, for example, in any constant random variable, if you consider any constant random variable, uh, I mean, if G is equal to x phi omega, so in this another comment I just want to make here. So if G is equal to this trivial, not phi, I am wrongly telling, it's null set. If G is equal to null set and omega, trivial sigma algebra, then any constant random variable is G measure.